All right, so the proposition is that a density matrix M is an extreme point in the space of density matrices where density matrices are convex if and only if M is equal to, so M's extreme point, if and only if M is the projection, the orthogonal projection map for some psi in Cn with unit modulus. So the proof is the following. So first of all, we're going to prove that if, okay, so we're going to first prove that if M is equal to P psi, then M is an extreme point. So we're going to prove that P psi is an extreme point in the space of density matrices. So what this entails is the following. So suppose that M1 and M2, so suppose that there exists M1 and M2, which are density matrices, and a real number alpha strictly between 0 and 1, such that P psi is equal to this convex combination of M1 and M2. Okay, so claim is of course that M1 equals M2 is equal to P psi. So what's the proof? The basic idea is, okay, so let's actually have a think about what P psi actually does, right? So P psi, right, what it does is it projects the entire space onto psi, right? So say that this is psi right here, okay? What this does is, in the orthogonal complement of psi, everything gets crushed to 0, right? Now, in the one dimension that remains, which is the span of psi, in the one dimension which does remain, we've got that P psi sends psi to psi. So, essentially in this one-dimensional subspace, P psi acts as an identity. Okay, but everywhere else, or rather in the orthogonal complement, it's just the 0 matrix. Okay, so we want to show that M1 and M2 does the same exact thing. So Cn is the direct sum of the orthogonal complement of psi and the span of psi, and I'm just going to write it like this, sort of abusing notation. Okay, now first claim is that the kernel, so the kernel of M1 equals the kernel of M2 equals the complement of psi. Right, so that's the first thing we want to show. So in other words, we want to show that M psi, we want to show that M phi is equal to 0 if phi belongs to psi complement, and same for M2, so MK of this is, okay? So to first prove this, right, we need to do something a little bit, we need to prove something a little bit weaker, namely that if phi is in the orthogonal complement of psi, then the inner product of M1 phi with phi is equal to 0, and same for M2. Okay, that's the first thing we want to prove. Okay? Yeah. So what's the proof of this? So, by the way, this has the interpretation that if I have a vector phi that's in the orthogonal complement of psi, so, maybe in this plane right here, then it's going to go to a vector that's perpendicular to it. And in fact, we're going to show that the vector that it goes to will be the 0 vector. 0 is orthogonal to every vector. Okay? So the proof of this is pretty straightforward, right? So we're assuming that pk is equal to m1 times alpha m1 plus 1 minus alpha m2. Okay? So if I take pk times phi, oh no, not pk, sorry, p psi, right, onto the projection of psi, this is equal to 0, obviously, right, because we're in the orthogonal complement of psi, so the projection map is going to, the projection map is going to take us to 0, right? The projection of any vector in this plane, this is perpendicular, is going to be 0. So anyway, so that's definitely the case. So that means that alpha m1 phi plus 1 minus alpha m2 phi is equal to 0. Okay, we're kind of getting there, right? So ideally we'd like to show that these two guys are 0, but we're going to have to prove this first. So let's just take inner product, right? So let's take this inner product with, let's take this inner product with phi, right? Now, this left-hand side, this guy is equal to 0, so this inner product is going to just give us 0, okay? And so, from using the linearity of the inner product, we get this. Well, linearity in the first argument, rather. We get this. Now, the next step would just be to notice, okay, M1 and M2 are density matrices, so this is non-negative and this is non-negative. The only way for this combination to equal 0, because alpha is strictly bigger than 0 and it's strictly less than 1, the only way for this to equal 0 is if this guy is equal to 0 and so is this. And that proves this. Now, to prove that m1 phi is equal to 0 and m2 phi is equal to 0, let's focus on m1 first. So the natural thing to do would be to try and prove this. But instead, we're going to we're going to be a little bit more general and try to prove that this is equal to 0 for any psi in Cn, right? Because that certainly implies that m1 phi is negative, is equal to 0. Okay, so this is often the penultimate step. If you're using the inner product, this is often the penultimate step to show that a vector is 0, right? To show that it's orthogonal to every other vector in Cn. Okay? Now, it's a little bit tricky how we're going to get there, right? Well, what we have to do is we have to use the fact that M1 is a density matrix, so we know that M1 Z inner product with Z is greater than or equal to 0. Okay? So to be able to get this out of this, right, we're going to put a linear combination of phi and psi and zeta in there. So namely, we're going to put M1 times beta phi plus psi, comma, beta phi plus psi, plus zeta, sorry, or whatever. No, okay, yeah, plus psi, sorry, I think this letter is. So this is greater than or equal to 0, okay? Now, let's use linearity and all that. So the first term is going to be beta, and then this argument is antilinear, so this is beta complex conjugate, m1 phi, comma, phi, okay? Plus, now this is beta m1 phi, comma, psi, plus m1 psi, comma, beta phi. This beta comes out as a complex conjugate, And actually, it's okay, I'll deal with this in a second. Plus, and then the final term is m1 psi with psi is greater than or equal to 0. Okay? Now, the trick is to try and get something like this appearing in here, right? Well, we know that m1 is Hermitian, so we can throw the m1 to the other side, self-adjoint, right? And then, at the expense of picking up a complex conjugate, we can swap this around. So we get this. Okay? And this is just squared. Okay? So, what does this tell us? So, well, we've already proven, so remember, don't forget that phi is in psi complement. So actually, this is 0. Okay? So we're left with this, and this is nothing but 2 times the real part of beta inner product m1 phi with psi plus m1 psi with psi is greater than or equal to 0. Okay? And so, we wish to prove that actually this guy must be equal to 0. Why must this be equal to 0? Well, this holds for all beta. Okay? So, in particular, if this were non-zero, then we'd be able to find a beta such that this inequality would be broken. And so that proves this being equal to 0. And then you can choose psi in particular to be m1 phi to conclude that m1 phi is equal to 0. Now finally, our final claim is to prove that, and obviously this is true for m2 as well, everything. Now we've got this. Okay, so for the final claim, there's not actually that much left, right? So the idea is that, okay, m1 is Hermitian, so we can think about its eigenvectors and eigenvalues, and we know that all but one of the eigenvalues are 0, right? So all of them are 0 except for 1, right? And we know that the trace of m1, and same for m2, which is the sum of the eigenvalues, must be equal to 1. So that would give us that the eigenvalue associated with the span of psi will have to be equal to 1, right? So this is now to be a little bit more rigorous. This is how we argue it, okay? We've got that m1 psi with phi, okay, is equal to 0 for any phi that's in the orthogonal complement of psi, right? Now, since m1 is self-adjoint, it's Hermitian, this is true, right? And so what does this tell us? It tells us that m1 phi, hang on, sorry. So we know that m1, okay, so sorry, okay, so we know that m1 phi with psi is equal to 0, right? So that means, using the self-adjointness and all that, we know that m1 psi with phi is equal to 0. Okay? So in particular, this is true for m1, so psi with phi is equal to 0, for any phi in the orthogonal complement of psi. Okay, so we know this, right? So that means that m1 psi belongs to the orthogonal complement of phi, right? Which, well, it's a subset. This belongs to psi complement, which is psi. So that means that m1 psi must belong to the span of psi. So that's first. So this establishes that psi is indeed an eigenvector of m1, right? That's the first thing we really have to check. Okay? So there is a beta naught that's complex number such that m1 psi is equal to beta naught times psi. And if we take any orthonormal basis up to n1, that's the basis for psi orthogonal complement, then the trace of m1, right, must equal to, well, we know that it must equal to this sum right here, and then I just separate out the last term. Okay, I'm calling it mk just so it's true for k is equal to 1 or 2. And now these guys are all equal to 0. This is equal to beta naught. But then that means that beta naught is equal to 1 because the trace of mk is equal to 1. Okay? Now finally, we want to prove, put the nail in the coffin in this thing and prove the statement. So here's the idea. Let psi be in Cn and consider the vector phi2, which is given by this. So it's the projection. Okay? It's the projection in psi of phi, right? That's what I call phi2. And phi1, let's call that psi minus phi2. Okay? So, phi2 basically, phi2 will be p psi on psi, and phi1 will be the identity minus p psi on psi. Okay, so clearly this guy will belong to the span of psi, and this will belong to the orthogonal complement of the span of psi. So this one might be a little bit trickier to see. Well, this is just psi minus. Okay, so yeah, so this is because, right. This is, by the way, yeah. Anyway, never mind. This is kind of reminding me of how we had the P1 up to Pk and they all added to the identity. So I guess this is a generalization of what we're doing here. But anyway, yeah, why is this true? Let's just see that. Well, okay, that's just, so psi minus pi psi with, right, so this is equal to minus, and this is nothing but hang on. oh, times by, hang on. So p of psi, this is equal to, with psi, oh, okay, so this is psi right here. This is 1, and so this is equal to 0, yeah, okay, so that's why. So if I look at mk acting on an arbitrary vector psi, this can be written as mk of phi 1 plus mk of phi 2, right? Where phi 1 and phi 2 are split up in this manner, right? Now this one, well, this phi 1 belongs to, yes, so, yeah, so this is equal to 0 from our claim that mk acting on the orthogonal complement of psi gave us 0, and this is equal to phi 2 from the other statement, but that is nothing but this, and we're done. That's the proof. So we proved that, well, okay, so what have we proven? We've proven that if m is equal to p psi, then we've got an extreme point, right? What about the other way round? Suppose that it is an extreme point. How do we know that m must equal to p psi? Okay, that's a little bit tricky. Okay, I'm not sure they've addressed that. They must have. Anyway, I'm done.